Okay. All right. We continue from previous lectures. So much that we have discussed on examples of many biosignals. So the main part here is to do the signal processing. Okay. I will upload some book reference in UKM folio where I haven't uploaded. I just want to show you this is the reference that I'm referring. Biomedical Signal Analysis, Chapter 18 from Standard Handbook of Biomedical Engineering. Okay. The other reference that I want to upload will be the fundamentals of biosignals. This one, I have both of these PDF files not yet uploaded, but I will put by today lah. Okay, and the fundamentals of signal processing, biosignals that is present is in analog format. Analog means continuous. So first step you have to do in order for you to do the processing, you need to digitize it. So it involves fundamentals of signal digitization, which is conversion from analog to digital lah. So when you involve with digitization, the sampling frequency must be obeyed, where you follow the Nyquist theorem. It must be more than twice the signal frequency. Okay, and then you do the pre-processing, including remove the noise using non-linear filter, or you can also use linear filter. You can also use adaptive filters, and you can also use digital filters. Digital filters means the kind of filters by programming lah. You can also do adaptive filters by programming also. The non-linear and linear filters are filters in terms of circuitry. So when you construct your instrumentation device, you have to include filter system. Using either active circuit or passive filters in your part of the signal acquisition. Okay, once you get the data, you need to do statistical signal processing. Statistical signal processing means you perform statistics on the acquired data. Okay, after you do the statistical analysis, you need to validate the signals. From the validation, you can do the feature extraction. Feature extraction means you want to quantify, you want to segregate the type of signal, whether the signal is normal or having some problems. Like for example, in previous class sharing session by Dr. Hidayah, she has shown ECG signal processing for her PhD work, where she focused on identification of the feature for atrial fibrillation. So her reference signal is ECG, her signal of interest is PPG. So she wanted to dig, or she wanted to highlight the difference in the PPG signals, which indicates atrial fibrillation problem. So that is what feature extraction. You obtain the significant feature from a signal. That feature indicates the characteristics of the signals. Okay, Yeah, from feature extraction, you can do also classification of the signal. Classification means you class it whether a normal signal or abnormal signal, so that you can identify the signal is a healthy signal or a signal of a person with illness. Because from naked eyes, you saw this, you see the signal, you cannot identify obviously, so you need to do signal processing by computation. So that's the job of the engineers, to do the processing, extract the important features from the signals. Okay, and the last one, the last two process, data compression and segmentation. Segmentation is actually part of signal, part of process whereby if the signal is too long, you can do processing by segmentation, meaning that you do part by part. If the signal is too long, you do you segmentize it. So you break into short signals and then you repeat the same process of signal processing on the next consecutive segments, so that you can have an overall. Without segmentation, the programming will be very long. This is very good for analysis of EEG signal, because EEG signals you need to do long time monitoring. Different from ECG signal. ECG signal, you have few heartbeats and you analyze based on few pulses only, because ECG signal is rhythmic signals. You have the pattern, but for EEG, the brain signal, because it does not have a specific pattern, you need to do a long-term monitoring. So it ends up that the EEG signals will be very long. So the processing of an EEG signal will be tedious, so difficult to handle. For example, if you have a MATLAB program, you run on a 1 hour data, it will be a long time processing. So to avoid, sometimes you can have the program hang because of too long. So you need to segmentize the big data into portion by portion. So you just process one segment. The next process, after finished the first segment, you move on to the next segment. And then after, and so on, so that it avoids programming that becomes suddenly hang, or problems dealing with data that is too big. Data compression is the opposite of segmentation. Data compression, if you have signal recording with very high frequency, so it will consume a lot of space. So you cannot cope with having too large data. So you can compress the data. You will change the sampling frequency of the data. Sometimes you need to do that because of if the data is too big. Because you can remember data that is very large, especially like the EEG signal. ECG both. ECG we have 12 electrode system. So each data is, say for example, you record for 10 minutes ECG, one channel. But when you have 12 channels, so you will have a lot of space for the data. If you record the ECG data high frequency, for example, high sampling frequency, for example, you have 1000 samples every second. So if you have 12 channels, and each channel represents the electrical activity from different region of the heart. So all 12 channels are important. So However, you just need to extract a few pulses from that 10 minutes data. So you can do the data compression. So one of method to do data compression is you change the sampling frequency from 1000 hertz maybe to 100 hertz only, because it will be sufficient. When you record, it's important that you record good to record with high frequency, sampling frequency. But when it comes to the processing, you need to manipulate the data depending on the situations. Same thing with the EEG signals. EEG signals, we have the 1020 system. If you do bipolar montage, right side of the brain, you have the every 4 chains, every 4 adjacent electrodes, you have 1 chain, right? So you have like 16 recording. 4 is for 1 chain. So you have a picture, sort of like a picture of the activities of the brain from one side, middle side, and then the back side, and so on. So you can also do data compression for the EEG data. For PPG data, because the nature of the system for PPG signal, you record from one sensor only. So you do not have too many data. And however, a lot of things can be done on this PPG signal. Okay. The processing can be done either in frequency domain or in time frequency analysis. Our naked eyes can see the signals in time domain only. So time domain means masa lah. You know the signal is moving across time. So you can see at, for example, start of recording, what happens after 1 second, 2 seconds, and then after a few minutes. So you can see the time domain signal with your naked eyes. You cannot see the changes in terms of the frequency. For EEG signals, trained medical doctors, they can identify the frequency of the signals quickly, even using their naked eyes, because they have been trained. They can see, oh, this signal is like an alpha wave. Alpha waves has a frequency around 4 to 8 hertz. Delta is below 4. Theta is even smaller than 1 hertz. So how they do it, they look at the cycle. In the time domain, they will see like changing pattern, and they estimate the time. So if they see, they know the speed of the recording, so they have the time frame reference, and they can see, they can estimate like 3 hertz theta waves. But for us, we are not trained. We can see changing, but we cannot identify. But if you are taught how to extract the frequency, a rough estimation only. So the frequency domain analysis and accurate analysis can be done by computation, by programming. So you can identify exactly what frequency the signal is having and what changes. Okay. You can also do time frequency analysis. Time frequency means you analyze both the time domain and also the frequency domain. Another method for signal processing is by doing pattern recognition. Pattern recognition, you look at the trend, trend detection and also event detection. Trend means you observe the kind of signals, how it change with time. Like for example, when you compare EEG and ECG, the trend for EEG, it has no specific rhythm. But for ECG, you know the trend of the signal, it must has a specific rhythm of PQRST, PQRST, PQR, and so on. So as the PPG signals, you have a specific trend. Okay, event detection is like for EEG signals, you observe epileptiforms from the EEG signal. So, and when there is an epileptiforms, you expect the person may have the chance to get a seizure. So, the epileptiform or the discharge within any channel of the EEG becomes an event-related signal. So that is how you do event detection. Okay. So people, depending on the nature of the signals, the approach of the signal processing depends on the situation, on what. So before you can perform the signal processing, you have to have a basic knowledge of the signals. You understand the nature, then decide on an appropriate signal processing. Okay, you can also do fuzzy logic programming. Fuzzy logic involves artificial neural network or machine learning, and we can also have artificial neural networks. In artificial neural networks, you need to have trained data, and then you need to test the data. So you need to have quite many data. You cannot have one single data. So for neural network. Okay. For using the fuzzy logic and artificial neural network (ANN), you can have you can produce your own expert systems. In the expert system, you can generate your own rule-based system. These are all depends on the collection of data. So to have to produce an expert system, you need to have reference signals. So the reference signals normally, because for biomedical engineering, the nature of the work is to help or to assist the medical doctors, especially in the signal processing, to obtain specific abnormalities, to identify if there is abnormalities or illness or disease from the signals. The doctor can identify those. Okay, and some methods dealing with genetic and evolutionary methods can be done. This is a higher level programming actually. And in all signal processing, it involves decision support and also decision making. Decision making when it comes to classification of the signal, whether it is a normal signal or abnormal signals, and so on, in order to make a decision whether healthy or not lah. Okay. You will be also dealing with signal modeling. Modeling means you represent a system based on a model. So for example, you have a respiratory system. This respiratory system has input from the brain. So you want to model a respiratory system. Then you have to have input from the brain and input from external and so on. And the output of the respiratory system is the concentration of oxygen, concentration of carbon dioxide as the byproduct. So you do the signal modeling. Many people do signal modeling using mathematical equations. That is one way. You can also use signal modeling by electrical model. Like for example, a sensor can be represented as of capacitor and resistor model from sensor. Like for example, I show you, not this one. Okay, this is going to be this is a diaphragm microphone for stethoscope model. The basics of stethoscope is simply must have diaphragm. The vibration of the diaphragm amplified the sound of the coming from the vibration, and through the earpiece you can listen to the sound. That sound is actually the sound from the heart, and with your naked ear you cannot listen to the sounds of the heart. If you put your ear close to the chest, you can hear, but still not clear. So using a stethoscope, the model for the stethoscope has a diaphragm that is very sensitive to movement of the chest wall, because you place the stethoscope diaphragm right on the chest. It collects the vibration of the chest due to the heart sound, because the sound from the heart is actually coming from closing of the valves inside the heart. Remember I showed you the videos, ECG videos, four chambers with 4 valves between chambers. So there are actually the 4 heart sound, but you can only listen to 2 heart sound, and those are actually can be picked up by the stethoscope piece. And inside the stethoscope you have an amplifier, a built-in amplifier. Okay. Wavelet and filter banks. Wavelet is processing in the frequency domain. You can convert the signals into wavelets energy, and then you observe the signals. This is can be done for any signals. Some people do wavelet signal processing on ECG signals, EEG signals also, and the PPG also. The principal component analysis is extracting the principal components from the signals. So you do PCA and you identify how many principal components are present. Normally you take the component that has the biggest, sometimes you may have like 10 main components. So from the 10 components, you need to identify the cutoff, which signals, which of the components that you want to focus on the analysis. Sometimes from like 15, 20 principal components, you can only use 3 PCA from the, depending on the content. Okay. When you haven't had the experience of dealing with the signal, it's quite difficult to understand what are these. So when you deal with the signal, then you understand what is PCA about and how to. That's why we have to include a project in this course. Instead of principal component, you can also do independent component analysis. So from the principal component, you identify a component that is independent of each other. So by taking the independent component, you focus on that component only. Then you observe, you analyze the trend of change in the ICA. Okay. Then you can also do support vector machine. This one is also part of artificial intelligence, because you can do a support vector machine. This involves mathematical transformation of the signals, and you do the support. There is a specific formulas for support vector machine, and for you all, normally you use MATLAB programming to do the support vector machine. There is a toolbox for support vector machine. So you just implement the support vector machine using the MATLAB. Okay, you can also involve with clustering the signals, chaos, and also non-linear dynamics, and do complexity and fractal analysis. So from those many kind of analysis, you need to choose the right method for the right problem. Okay. So how do we do classification of the signal? We can classify the signals on the basis of few feature, based on the signal characteristics, based on the signal source, or you can based on the application itself. So if you do based on signal characteristics, this is based on technical point of view only. If you base on signal source, it will be from looking at the source of the signals and how the signal is originated and how it is measured. Like for example, you know the heart signals, ECG signals, the source of the signal is from the SA nodes. So the electric signals originated at the SA nodes. So SA node must always send impulses to the AV node. So if there is a missing P wave or a P following a P wave, there is no QRST. So you know roughly that signal from P do not go downwards. Suddenly you can have another P waves, meaning that signal from SA node arrive again without the signal distributed to the rest of the heart. So there is no QRS. Okay, so you know the source must be the signal source. Based on application, for example, if it is based on neurophysiology, straight away you know you have to take the EEG signal. If you want to classify cardiology problem, straight away you will do signal processing on ECG signals, or you can also use PPG signals, because PPG signal is very correlate with the ECG signals. You cannot, you want to apply signal analysis on cardiology, but suddenly you evaluate the EEG signal. So that is not appropriate, because EEG signals is pertaining to the brain activities. So this is important. So you need to know the application. Okay, and also if it is for monitoring, you need to have monitoring for how long. And if it is for diagnosis, what you want to diagnose, specific problems related to what. So all are these you need to consider before you can classify the signals. Classification may be helpful in the selection of the processing methods as well. Okay, signals in general, it can be differentiated. It can be composed of two kinds of signals, whether it is a deterministic or stochastic. A deterministic signal is signals that is periodic, and also it can be a non-periodic. A periodic signal can be complex. Non-periodic signals can be almost periodic and can be a transient signals. Transient signals mean signal that reach to a certain level. Okay. Stochastic signals can be signals that is stationary and non-stationary. These are actually definition of general signals, not related, not indicating biosignals. In general, this is how you can differentiate signal types. Okay, deterministic may be accurately described mathematically, usually predictable, and it is rarely a chaotic signal. Periodic means you can represent the periodic signals in digital form by equations. For example, ST is equal to ST plus N plus NT. This is Fourier series, kan? You can represent signal in terms of mathematics equation. Almost periodic, the patterns repeat with some irregularity. It is not actually periodic, but it has irregular pattern in the signal. So that's why it is not totally periodic. It's called as almost periodic. Transient signal has the characteristics it changes with time. It changes with time, actually with a long time, until it reach a stable value. That is transient. Sama macam you belajar electrical transient response lah. First order system, second order system, it can has a transient response. Behavior of a capacitor charging ataupun capacitor discharge. That is the transient response. Reaching a certain level, it will become static over time. Okay, stochastics defined by their statistical properties. Okay, so for stochastic signals, the best analysis is to conduct statistical analysis. You look at the distribution. For stationary signals, signal that is not changing over time. The signal is same value over the time. Okay, ergodic is having statistical properties of the signal that may be computed along time distributions. These are all definitions sajalah. So that when you come across, you tak adalah terkejut kan. Okay, all biosignals may be considered stochastic because one person to the next person, they do not have exactly the same value. It is changing, but with a similar pattern, similar feature. For those who have problem, then the signal becomes different. So, but they look similar. They look so. It's the job of the doctors to identify from the signals what are the problems, what are the difference, which is difficult for them actually. Almost deterministic. Sometimes the biosignals can also be almost deterministic. For example, the ECG signals, the wave shapes that almost repeat themselves. And the characterization is often by detection of the certain measures of the waves. Truly stochastic signal is the EEG signal. Meaning that it's not at all repetition, just changing and changing. So the best to do analysis for EEG is statistical properties. Okay. Biosignal application domain, information gathering, measurement of phenomenon to understand the system. And the diagnosis is in the diagnosis stage, you want to detect malfunction or pathology or abnormality in the from the signal. So these are the purpose of conducting the biosignals. Okay, you can also do biosignal analysis for monitoring purpose. So there are three main objectives lah. Another, I think, 5 actually, for therapy and control and for evaluation. So if you want to do for information gathering only, you keep it as record. For diagnosis, you need to identify the malfunction from the signals. For monitoring, is just to observe the changes over time. Obtain the continuous or periodic information about the system. Therapy and control, you modify the behavior of the systems and then you ensure the results. That is for therapy and control application. And the 5th application domain or objective is to evaluate, evaluation process, the objective analysis, proof of performance, quality control, and the effect of treatment. Because sometimes after you, after the person has been seeing the doctor, taking medication, you want to confirm the person is already healthy. So you need to do analysis of them as a proof of performance that the person is now healthy again, or at least better than previous time where they just come to the hospital. Okay. Now we look at issues or problems in biosignal processing. There are few issues. One of it is accessibility, patient safety, preference for non-invasive systems. So difficult to obtain biosignals from a person because most people, they don't want system that is invasive, taking the data from the inside of the body. So they prefer a non-invasive system. But non-invasive system mostly do not record actual process inside the body. But because of the preference, because of discomfort lah, non-invasively, it's most of the time is comfortable because that does not involve cut open the body surface or area of the body. So you do simply recording from outside, from external. So that is why people are more comfortable with that. But once you put a needle in the hand, number one is painful and then not comfortable lah. So to get a biosignal is quite difficult in terms of not accessible lah. And the problem with the non-invasive system, it is not a direct measurement. The variable of interest are most of the time not directly obtained. So you need to refer to the reference signal also. And then biosignals has issues of variance. Different people taking data may produce different results, and the variance of the data is due to inter-observer variance or intra-observer variance. Okay, inter-observer means person A record blood pressure. She obtained 120/80, for example. Another person B or medical doctor B, take the blood pressure. He thinks the blood pressure is 125, and the 125/85, for example, different from Dr. A tadi. So that is inter-observer variance. The result of the data taking is not the same, vary from one person to another. Intra-observer variance is same person taking the data but at different time produce different results. So that is also not good because the person does not experience any changes. So by right, the data from that same person should be the same lah. The person taking the data, same person, same subject. The only difference is time. Mungkin the first measurement is done pukul 9 pagi. The next measurement is done pukul 10. Tapi data dah berubah dah. Ataupun kalau tak banyak masa beza, mungkin after 10 minutes ke, when taking, the data may not be exactly the same. So that is intra-observer variance. Okay, and the interrelationships and the interactions among the physiological system itself can produce, can affect the signal behavior. So that because our body is having its own system that need to maintain homeostasis. So the interrelationship among the organs in the body always affecting other sub organs. Okay, subsystems of interest may not be isolated because the body interact. Organ systems in the body interact with each other. As simple as when you feel excited, your heart starts beating because your brain is telling you, telling the heart to beat faster. Once your heart is beating faster, your breathing also increase. Breathing rate increase because of interaction between the nervous system, the brain, the respiratory system, and the heart itself. So you cannot avoid the interrelationships and the interactions among the physiological system. Okay, acquisition interference. This one is external factors. The instrumentation and procedures modify the system or its state. For example, if you do recording in the area of high magnetic field, maybe your data can be affected. So this acquisition interference can be avoided. You can take precaution to minimize it. Okay. Interference tadi. Interference regarding interrelation among physiological systems can produce artifacts in the signals. For example, when you are recording EEG and you have muscle artifacts. Sama lah juga if you are recording ECG, if the person is moving, suddenly you see muscle artifact in the ECG signals. So low level voltage EEG require very sensitive amplifiers. They are easily sensitive to interference too. And you have limited possibilities for shielding or other protection, non-linearity, and obscure the system under study. Okay, and then we have basically all biological systems exhibit non-linearities. Okay, while most of the methods are based on assumptions of linearity, because we are easy to handle linear system, we always assume linear. Even for mathematical equations to solve, you consider a linear system. However, our body system, most of the time, they are not linear. They have non-linear. So, assuming a non-linear system into close to linear may produce inaccurate analysis. But scientists have always assumed linear system. From the linear system, they improve little by little, because if you know if the system is totally non-linear, you don't have difficult to start the analysis. So somehow you need to start the analysis, then you improve from that first analysis and so on. So we consider close to linear first, and then you input the element of non-linearity in the analysis in order for us to do the approximation. The exact structures and true functions of many physiological systems are often not known. That is the challenge for us to evaluate the biological system. Okay, how we can do data acquisitions or signal acquisition. We need to have a digital system where we have a transducer. You transduce the analog signals to digital signals, and you amplify the signals. You digitize it so that you have analog to digital filter, and then you have AD converter, and then you have the digital signal. Once you get the digital signals, you can do computation by programming. Okay, and after the processing, you can do classification. You can do if you want to display the signal or display the results, you can have a display in terms of end user meaningful format lah. Sometimes you want to also monitor the signal in the time domain that is changing over time. Sort of you display the collected data as a reference. Okay. Okay, short-term HRV. HRV stand for heart rate variability, and BPV. BPV stand for blood pressure variation. So this example shows the plot shows actually the bottom one is millimeter mercury, which is blood pressure. The middle plot is beat per minute, which is heart rate, and the top one is the respiration. Okay. This is an example of interaction between a few biosignal parameters. Application of signal processing, other than biosignal analysis, there are many. All areas involve signal processing, such as even in the entertainment pun, you want to produce music that is very clear, free from noise. So you need to remove noise from the signal. You have to filter. So you do also the sound engineer has worked out the system so that microphone tu yang diguna oleh penyanyi dah filter out the noise so that the voice coming out from the microphone, all noises will be removed. So you have actually they have done the signal processing prior to final application of the microphone and the speaker itself. It is also common to do signal processing in communications, because when you for communication you send data and then that data can be many kinds. Data that is secret data, or you need to encode the data and then you decode. You need to do the signal processing also. Space exploration, of course, there are images of space. You need to do the signal processing so that you can have clear image, filter this and filter that and so on. Same thing with the medicine and archaeology. Even archaeology data from many years, you need to do processing also. And the signal processing is driven by the convergence of communications, computers, and signal processing. Signal processing is benefited from a close coupling between theory, application, and technologies for implementing signal processing systems. And signal processing is concerned with the representation, transformation, and manipulation of the signals and the information that the signal contain. So the signal processing itself is actually a very huge area. You can do lots of things. And signal processing can be inside the signal processing, you can do image processing also. And we can have continuous and digital signal processing. In the early days, prior to 1960s, most of the signal analysis are done in analog form, because at that time, computers are not available yet. Even in the 1970s, a computer processor size of a processor for a computer in the 1970s is the size of a room. But nowadays, you have your telephone. You have a processor in the telephone, smartphone. It's like your computer. So the technologies, electronic technology advancement, making digital world is available to everybody. Digital signal processing is caused by sequence of finite precision numbers. Important theoretical developments such as fast Fourier transforms, so that you can conduct the analysis in digitization. And with digital world, it helps people to do, because computer can do fast processing compared to our brain. Our brain ni simple mathematics boleh lah, tapi kalau computation yang need to repeat the same thing over many times, so you let the computer do for you lah. So that is the beauty of computation. You can repeat, so within second you can analyze the signal. For example, like in the analog signals, it will take a long time, and it will be based on individual person's effort, and then you will have inter-observer yang tinggi for analog signal processing. For digital signal processing, the inter-observer kita dah remove, because computation satu program saja. So chances of inter-observer tak ada lah, because the same computer, the same look. Okay. And okay, in digital signal processing, signals are represented by sequence of finite precision numbers. Processing is implemented using digital computations, and digital signal processing is a special case of discrete time signal processing. So it's important to digitize the signal at the rate that is suitable without the loss of important information between data points. So you need to have an appropriate sampling frequency to digitize the signal, because you do the processing only on the finite value at finite time. In between the time sample, you don't have the data, so you don't know what's happening. So if your sampling time is too slow, for example, if you sample every 1 second, so maybe between 1 second to 1000 millisecond, which is equivalent to 1 second, maybe at minute 100 milliseconds, something has changed. Because inside our body, even if you look at the heartbeats, consider the heart rate is 60 beats per minute, every second 1 heartbeat, and the process of propagation of electrical signal from SA node sampai ke Purkinje fibers tu is only within 60 seconds, within 1 second, within 1000 millisecond. So the signal speed from SA to AV to bundle of His to the Purkinje fibers, the speed is not the same. The speed delay a little bit once it reach the AV node, and then it pick up the speed. When it reach the Purkinje fibers, it will be fired very fast. By the time another SA node, impulse from SA node transmit again to the AV, and then it repeats again. So within 1 second, many things happen. So if you sample, one sample on for heart rate, for ECG signal, you lost many information. Okay, digital signal processing is a special case of discrete time. Okay, that is what said just now. And digital and discrete. Okay, what is the difference between the digital and the discrete signal processing? Continuous time signal processing means time and signals are continuous. Discrete time signal processing means time is discrete, signal is continuous. Digital signal processing, time and signals are discrete. So there are three areas: continuous, purely continuous signals. Both the time and the signals are continuous. But for discrete time signal processing, the time is discrete, despite that the signal is still continuous. But digital signal processing, you digitize kan, you make the time and also the signal discrete values. So discrete time signal processing is intermediate between the continuous signal processing and the digital, because in digital signal processing, both the signals and the time has been changed to a discrete values. So people rarely do a discrete time. Nowadays, once we get the digital data, our system is digital signal processing lah. Kita tak jumpa pun discrete time signal. Okay. For discrete time processing, this is just for your information lah. Where we have continuous to digital conversion, you have a discrete time system, and then you can convert from digital to continuous. So real-time operation is often desirable. Output is computed at the same time, time rate at which the output is sampled. Definition of real-time, meaning that result is obtained within the time frame that is depending on the need of the system. So for example, you say the user has to define what is the allowable time for getting the result. So if it says, if he defines allowable time is 5 minutes, that means you can get the data within 5 minutes time, so it is a real time. You can get the results in real time. If you define 30 minutes is still real time, so that is considered real time for the user lah. So user time ni dia bergantung kepada needs, how long you allow the signal processing. But a true real-time system is almost immediately lah. Kalau you ambil data hari ni, then result dapat besok, that is not real time lah. Or maybe you get the data after 1 month, for example. That is totally not a real time. You do a post-processing. The time taking is especially in the signal processing. So for example, you get the data, record data from person, and then the programming will will analyze the signals. After 1 minute, you get the result. So the person is healthy or not healthy and so on. So that is considered real-time system. Objects of signal processing. The process one signal to obtain another signal. And signal interpretation is characterizations of the input signals. For example, in a speech recognition system, speech signal entered the digital pre-processing, where inside the digital pre-processing we have the filter and the parameter estimation. And then you do the pattern recognition, and then you do the phonemic transcription and enter an expert system, and you have the final signal interpretation. So for example, in the pattern recognition, there will be a collection of common voice pattern or common speech pattern. And from there, you can have the expert system to interpret the speech signals. The symbolic manipulation of signal processing expression. Signal and systems are represented and manipulated as abstract data objects without explicitly evaluating the data sequence. So this is not a direct, it is more of symbolic meanings. Rarely we seldom use symbolic manipulation. Okay. Now the need for digital signal processing, software such as MATLAB has many tools for signal processing. It seems that it is not necessary to know the details of this algorithm, such as the FFT, fast Fourier transform. It is a built-in function whereby you can simply use the fast Fourier transform algorithm in order for you to do signal processing using MATLAB. And a good understanding of the concepts of algorithms and principles is essential for intelligent use of signal processing software tools. So you just use the MATLAB as a tool that can help you analyze the signal. Okay, the extension of signal processing, you can do many things. Multi-dimensional signal processing, you can do spectral analysis, signal modeling. Signal modeling tu dah sebut dah, tapi modeling is actually a big area. Okay, adaptive signal processing, specialized filter design, specialized algorithm for evaluation of Fourier transforms, and specialized filter structure, multivariate signal processing, and wavelet transform. So those are very extended signal processing. For you all, we are expecting students have the experience of dealing with biosignals and plan for appropriate analysis, and then results of the analysis, do classification and do validation and present the project lah. Okay, that's all for the lecture today. I think I have video next week ya, satu minggu lagi. Kalau tak, the following week with Dr. Kalai. And okay, today we finish early because I finished the lecture, previous lecture. I'm sorry that I am a little bit delayed of uploading materials, but from previous teaching materials that I upload in the UCAM folio, make sure you all familiar because those materials will be very helpful for you all to understand the materials for the course. So any question? Okay, ada jalan. Maka mesti bukan apa. Oh, siapa ni? Dia tak boleh masuk ni. Anas Haziq. Let me add. Macam mana nak add? Saya cuba add sekarang. Manage team. Can't find match A. Kat depan ni. Find, jumpa tak? Oh, A1. Tak jumpa lah. Anas Haziq dia dalam ni, dia boleh masuk ni. Anas, cuba bercakap sikit. Siapa nama dalam ni? Tengok members. Tak berjumpa. Ni ke? Nazahan. Anas ada dalam ni tak? Macam mana dia hantar mesej kalau dia tak boleh masuk?
Doktor,
Ya.
yang tak boleh masuk tu Muhammad Farhan.
Oh, Farhan, okey.
Dia sampaikan je.
Oh, Anas yang hantar mesej.
Ya, doktor.
Okey, bagi pihak Farhan. Okey. ID dia ni kan? 1A162671 tu.
Ya kot.
Saya cuba search kat sini. Saya paste. Tapi tak berjumpa ni. Can't find. Saya boleh masukkan dia sebagai email, diguna email, bukan email siswa, tapi dia akan jadi guest sajalah, tapi still boleh guna. Ada je student international yang tak daftar UKM sebab dia tak boleh masuk ke Malaysia sebab COVID-19, tapi dia orang dah start semester. So dia tak ada email siswa. Jadi dia gunalah email Gmail ke apa, boleh add dia dalam kelas sebagai guest lah. Nanti Anas tanya Farhan, ada email lain tak selain daripada siswa email ni? Boleh kan?
Okey doktor, nanti saya sampaikan.
Okay, ada soalan lain? So I promise this coming Thursday, we will do a quiz, Kahoot . Hopefully it will be interesting. Quiz tu, let me see. Tengok kita punya plan for the semester. Mana? This one. Okay, saya cepatkan sikit quiz lah. Oh, I have another demo. Okay, maybe I will do today on EEG. Okay, I lupa dah. Demo on EEG. Mana? I put that demo slide on iFolio already. Okay, I will do this now. Okay. Okay, actually, this one has been done by my ex-student lah, Muhammad Syakir, your super senior lah. He has involved with me on EEG analysis for his master study. He completed in 2018. He joined as a master student right after graduation, 2016. He was my FYP student actually, but his FYP was not on ECG. Was not on the EEG. He was doing PPG study, but when it comes to master, I invite him. Why not you explore EEG? So it would be interesting. And he take the challenge after 6 semesters. So, his graduation delayed by 1 year. By right, a master study is only 4 semesters. But because he had difficulties publication that time, so on the 6th semester, he had his viva. But still quite fast lah, considered as he start with zero knowledge on EEG, but his achievement is very good, and he has from no knowledge regarding EEG, he completed his master, and he had, if you ask him regarding EEG, he can tell many things. Okay, let's recall. EEG stands for electroencephalography. Electro means electric, encephalo is the brain itself, graphy is the process of getting the signal. So in sentence we can say EEG is the process to record the electrical activity of the brain. So this one is the nerve muscles. Information transmit to the neuron in the forms of electrical signals. And this one is the cell body. And you have this one will be the axon terminal. So remember, for any neuron cells, conduct current one way only, from the dendrites to the cell body to the axon, and transmit to the next neuron. So, and neuron can be many kind. Sensory neurons, motor neurons, cognitive neurons, or neurons that is involved with emotional sensation. But the nature of a neuron is a standard form. So you can have many kinds of neurons, but that is not important because you are not studying neurons. You want to know EEG itself. Okay. Who use EEG? The neurologist. Okay, the neurologist is the doctor that specializes in the study and the treatment of disorders associated with the nervous system. They use the EEG to diagnose for cerebrovascular disease, meaning that cerebral is the brain, and the spreading of the blood circulation within the cerebral, such as illness due to stroke. So the distribution of blood circulation in the cerebral circulation is disturbed. Or you can they deal with people with Parkinson and Alzheimer's disease is a neurodegenerative disease. Parkinson's disease is certain part of the brain affected, menyebabkan orang tu akan menggigil-gigil untuk certain time. Dia tak boleh kawal muscle dia. So they will look at the EEG and identify which part, and they can they can do appropriate intervention to help the people with Parkinson's disease. Alzheimer's disease, Alzheimer's dalam bahasa Melayunya nyanyuk lah. Actually, old people who experience forgetful. People with Alzheimer's disease dia tak boleh recall memory yang dekat, yang baru berlaku. Yang lama-lama, yang bertahun-tahun masa dia kecil, dia ingat. That is Alzheimer's disease. So Alzheimer's disease is illness that cannot retain short-term memory. Okay. Epileptologists also use EEG, and epileptologists is actually neurologists who have gone through extra schooling process. They have been trained to specialize in the field of treating those with epilepsy. So epileptologists adalah pakar penyakit sawan, because they look at the EEG to identify if there is any abnormal feature from the EEG that they can help the people with the epilepsy. Because epilepsy is difficult to cure, what they can do is simply monitor. And Shakir's work was looking at EEG signal of a person having epilepsy issues. So his work was actually trying to identify epileptic forms from the EEG signal. So when you deal with EEG, you have to know the there are few terminology. EEG can be meaning electroencephalography, or it can also mean electroencephalograph. It can also mean electroencephalogram. So if the word graphy at the end is the process. If it is graph, it is the instrument. If it is cephalogram, is the recording system. The process itself. Not the process, the whole system. Okay. And the instrument with the EEG, we have electrodes, we have acquisition system, and we have facility to display the waveform. The facility to display normally on computer, or it can be printed, but they cannot afford to print all EEG sequence because it's going to be a lot. So normally they don't print. They can only print a specific page that they want to focus. Most of the EEG signals are stored as digital data. Later on, the doctors, the epileptologists, the neurologists only open the file and monitor from computer screen because they don't want to waste paper. For ECG, yes, most of the time, the doctors print on ECG chart, keep in file. But for EEG, they rarely print. The electrodes of the EEG is different from the ECG electrode. The electrode for EEG is small because you have to place on the head. For the 1020 system, you have almost 20 electrodes, including the reference electrode, the clip in the ear. You have auricular electrodes, left and right. Okay. And most of the electrode. You can have with either it's the gold standard electrodes, or you can have a quick setup electrodes. The gold standard electrodes are normally with gel inside, and the gel for the electrode is function to reduce resistance, skin resistance. Inside the gel, there will be electrolytes, and these electrolytes actually reduce the resistance, skin resistance, so that you can acquire the signal, the electric signal underneath the scalp, so that you can obtain strong signal so that you can display. Remember, the brain signal is very low voltage. It's in microvolt. ECG signals, amplitude of the ECG from the heart is much bigger than the EEG signal, because ECG signals are muscle type signal, whereas EEG signals are nerve signals. So the current that passes through the nerve is very small compared to the signals, electric signals from the heart. Okay, and the electrode placements, I've shown you few series of the recording. This one, the leftmost figure, is single channel EEG. So it's taken the forehead, and then the reference auricular A3 tak telinga kiri, jadi odd number kan. So A3 dengan FP1 lah, ni sebelah kiri. And maybe I think it's only one electrode. So medical doctors, neurologists, they don't trust this system. Only one channel is not sufficient. They want at least a 10-20 system. So that's why the 10-20 system is the standard measurement. This one is 10-10 system. 10-10 system has, I think, 50 electrodes. And you can have 100 channels, if I'm not mistaken. You can combine few connection, and this one tak ada orang pun nak buat kot. Only for research, yes. But for routine EEG, they don't use the 10-10 system. Okay. Because of 10-20 system as the gold standard for EEG measurement, you need to understand the 10-20 system is simply the electrode placement, 10% from the nation, and then 20%, 20% the next one, and so on. So from the center line to the temporal T is also 20%. And the ear is labeled as A1. This is left ear lah. So you have left ear, right ear. So by having this convention, you will have to use 20 electrodes altogether. And part of the brain, the level of the electrodes is based on the lobes of the brain. And if you look at the brain structure, we have a temporal lobe, occipital lobe at the back, parietal lobe at the side, and frontal lobe above your forehead. So if you move from forehead to back, you will have frontal lobe, parietal lobe, and then occipital. Di tepinya ada temporal lobe. So your electrode system, you will have F electrode, frontal, and you have T for temporal, C is center, and P for parietal, O for occipital. So O, the occipital is actually having the center for vision. So O1 and O2 has information regarding vision. And if you study the brain, there will be motor area, sensory area. Motor area will be near the frontal lobe, and sensory area will be in the parietal lobe. So the sensory and motor always map with each other, next to each other. So the brain has two hemispheres. So you have left hemisphere, right hemisphere, and the brain controls the body opposite side. For example, your right brain control your left side of the body. So sensory information from the left side enter the right brain, and the brain will give instructions to motor activity like muscles from the right brain to the left side of the body. So kalau cedera di sebelah kiri otak, bahagian sebelah kanan badan tu susah, tak boleh nak kawal lah. So people having stroke where injury happen in the left, the right side will be affected. If the right side is affected, the left side of the body is affected. So it's always opposite. That is just general knowledge lah. Related to the electrodes naming. So we have FPTO electrodes. So if you are dealing with EEG signals, you have to be certain which electrodes. Tekan N. Ada tadi. Okay. Okay. Okay, the brain, this is generally the parietal lobe, the processes, what are involved, occipital for visual processing. The bottom part of the heart, the brain is the cerebellum. The top here is called cerebrum, and cerebrum involves sensory and motor activities, and also emotion, feeling, and so on. Basic process, sensory and motor actions are basic process, understandable, easy to describe. But for emotions, it's higher level of brain processing, because emotions, we call it, it's only in human. In the low level like animals, they don't have emotion, but actually they do, but it's just that difficult to describe lah. Okay, the temporal lobe is responsible for apa pula ni? Hearing and language, whereas the frontal, cognitive function, and also memory. And the frontal lobe has the motor area lah. The parietal integration is the integration area, having the sensory area. So sensory means the feeling of pain, heat, and so on goes to the parietal, whereas action comes from the frontal lobe. Okay, the bottom part is the cerebellum. It's not involved in EEG because you have only taking the signal from the cerebral region only. Okay. The acquisition system of EEG must have amplification because the amplitude of the signal is very small. You need to amplify it. And it has a lot of noise, especially the muscle noise. So you need to filter. So and also issues regarding the position system for the EEG. You need to have a right sampling and storage. You need to store the EEG record. Principles of the EEG. We have layers of the brain. The EEG electrode is placed on the surface of the head, and the nerve is actually within under the skull. So there will be layers of the skull, and you will have neurons underneath it. Okay. The brain contains massive of number of neurons. The neurons are excitable cells which their activity can produce electrical fields. These electrical fields can be picked up by the electrodes, and EEG works by detecting the potential difference between the two electrodes. Similar to ECG, you record EEG signals based on 2 points. At least 1 point to the reference. But for EEG, we have bipolar montage. So you always record one electrode to the. So you take the difference only. The signal that you see is actually the difference between the 2 points. Okay, the concept of EEG is similar to the voltmeter. Okay, EEG montage. Here you will see FP1, F3. This is the left side. And then F3 to C3, C3 to P3, P3O1. So this will be one chain until you reach the center point. C is for the center. P is for the parietal. So you will have the frontal chain. You have the middle chain, temporal chain, and so on. So actually, okay, no. We have 4, 4, 4, 4, 16. And the bottom one, FZ, CZ, and CZ P3 is the center line. So this is frontal left chain, frontal right chain, frontal temporal back chain, right left side. This one temporal towards the back of the head, right side. This one is for bipolar montage. For the unipolar montage, unipolar means based on one single, but you have to make it in reference to an average of all electrodes. For the bipolar, always 2 electrodes per one channel. So it is actually the difference between the two channels. Whereas for unipolar montage, the referential connect to common electrodes such as the CZ, FZ, A1, and A2. Sometimes you use CZ or FZ for the reference. Sometimes you use the A1 or A2 for the reference. The average one is to subtract the average overall electrodes from each electrode for each time point. I normally see bipolar montage is used. So far, I have no experience dealing with unipolar montage. Because this is the common for epileptologists and neurologists, they know when to use the unipolar montage. In fact, Shakir's work is dealing with the bipolar montage. So the EEG signal itself, analysis can be done in the time domain. The EEG is non-linear, non-stationary, and very noisy. So this is the properties of the EEG. And this is the main challenge. Yet you have to come up with something. Okay. Saya nampak ada. Alright. Alright. Okay. The variables in the EEG is the morphology of the signal, the frequency of the signal, and the synchrony of the signal. Variables means pemboleh ubah yang kamu boleh ketengahkan. Like for morphology means shape. Frequency means the frequency component in each of the channel. Synchrony, whether each channel synchronized with each other or not. Okay, synchrony ni important because if few channels are synchronized with each other, meaning that source of signal come in the region with that same with having the synchrony. Signals that channel that do not have synchronization does not have that feature. So dari situ kita boleh identify origin of the signal tu. Because sometimes I'm talking about, for example, the epileptic forms. Sometimes it happens on maybe two channel, F1, F3 for example, and F3 and C3, but not F3, T3. So meaning that the location is only in the frontal side, not in the back side of the head. So that is synchrony. Okay. Shape of EEG, signal of interest for Shakir's work is epileptiform. Epileptiform is simply the discharge that is that is present in EEG sequence. So the characteristic of epileptiform, it has a shape of standard waveform macam ni lah, where you have depolarization, repolarization, and then depolarize yang slow transient, and then come back and so on. So knowing that this is the feature of a epileptiform, so he has to identify for spike and so on. What is the signal characteristic? Like for example, he label A, this point, P, peak point, B is when it goes down, C is the waveform naik tu, and then R wave, and then dies, the signal dies. So from here, he has to identify lah the amplitude of the spike. Okay, and he finds the slope of point AB, also find the amplitude or the average width of the spike. Okay. EEG frequency, we have delta waves, theta waves. Alpha is 8 to 12, bukan 4 lah. 4 to 8 tu adalah theta actually. Alpha wave is during conscious and during relaxed. Delta wave is obvious in babies. Theta wave is during sleep. If delta wave is present in a normal person during wakefulness, something is wrong with the person. This frequency, as I said just now, kalau macam ni 4 to 8 ni, simply doctor count. Katalah this time is 1 second. The time frame here is approximately 1 second. So ada turun naik sebanyak 4 kali. They say within 1 second, there is 4 cycle per second. So approximately it is 4 hertz signal. So they count simply like by observing the frequency. But for us, Actually that is not accurate lah. For us engineers, we want to know exactly what is the frequency kan. So to obtain the exact frequency, you need to do signal processing lah. You cannot simply observe with your eyes ni. So like this one, alpha waves, they count like 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, this is alpha wave. As long as the time frame is 1 second. So if the plot is 10 second, so they just zoom their eyes for 1 minute, 1 second, berapa banyak cycle. So dari situ dia nampak the cycle per second. Cycle per second, they call it cycle per second. But for us engineers, we call it units of hertz lah. Frequency unit. Beta waves is higher frequency, 20 to 40 hertz. Sometimes some book says 38. Above than the beta frequency is called the gamma frequency. The gamma is very high frequency. That is during active activities like calculation, performing mathematical calculation. But mostly during wakefulness, we have beta waves. Because when we start thinking and we switch our mind from one area to another area, processing, so we have a lot of beta wave. If you are very relaxed, you listen to music, you become calm, your brainwave can change its frequency to an alpha rhythm. And so on. This is the basics of EEG signals in terms of frequency interpretation. Okay, and these are the insufficiency, optimum, except what are the consequences lah. Like for example, alpha wave, if not sufficient, the person become is an indication of stress or anxiety. If it present at optimum level, the person feel relaxed. If too much, the person unable to focus and the person is not alert. For person who has a lot of beta waves, the cognitive process, if too little, cannot perform high level cognitive process. But beta wave is important for focus, memory, and problem solving. And if too much, beta wave can easily cause the person become panic or anxious or very stressful or tense. But when you have gamma wave, it's unable to learn. And learning, but because gamma is mostly important for learning process. And if too much gamma, that is an indicator of a stressed person. Kalau alpha ni too little, stress juga. Tapi kalau too much gamma, that is also indicator of stress juga. Yang low frequency delta ni, deep sleep and natural healing. So kalau you buat meditation, you can increase your delta level. Okay. Kelas bang? Tengah kelas? Okay. Okay, ada sikit je lagi. Kenapa ada pergi sini? have less than half. Just like to go. Oh, the time is 1 o'clock. Macam mana you all nak saya teruskan? Boleh. Ada masa ya? Kalau you ada masa, saya habiskan lah. Boleh ya? Okay. EEG synchrony, pattern of the signal, normal, complex. Kalau less complex, maksudnya dia jadi ada rhythm. Bila ada rhythm, dia tak, the complexity index dia drop. So this is common when happen in an epileptic person. Walaupun dia tak exactly having a specific rate, tapi dia jadi less complex compared to this one is complex. Turun naik, and then frekuensi tak sama and so on. Okay. EEG artifacts, physiological artifacts such as due to movement of the eyes, eye blinking, the muscle artifact, due to sweats and heart action and so on. Non-physiological defect or artifact due to the electrodes problems, amplify the noise from the electrode and also from 60 Hz power line. Sometimes cell phone artifact. Okay. The EEG signals during open eyes and closed eye are also different. So if you see here in a bipolar montage here, when it happens in any channel with the frontal, that indicates from the front side, which is close to the eyes. So this one is F8, F2. Anything with the F, channel yang tak ada F tu, tak ada deflection kan? So this is an obvious eye movement. Open eye, closed eye artifact. And it has a frequency, same frequency. Happen here, here for example, ni berapa? 1, 2, 3 heart rate, that means approximately 3 second lah kan? 1, 2, 3, 4. 3 to 4, every 3 to 4 second, dia buka mata, tutup mata, buka mata, tutup mata. Semua channel yang ada FP, sama ada FP1 atau F7, channel itulah yang terjejas. Itu menunjukkan ianya adalah daripada eye punya muscle. Okay. And then movement artifact. Semua channel bergerak. This one is diffuse muscle artifact. Rapid eye blinking. You will see semua channel involved juga lah. Karakteristik eye blinking ni memang daripada frontal electrode. Okay. Electrode ports, some channels has opposite, especially channel yang adjacent to each other. Okay, now engineering, what is engineers do in EEG analysis? Okay. The approach of an engineer always signal processing lah. They do pre-processing, signal transformation, feature extraction, and lastly the classification of the signal itself. The pre-processing involve filtering, normalization, and segmentation. Okay, normalization means you rescale the data between certain range, for example 0 to 100% or 0 to 1, so that because you don't want to have a variation of level, so an easy way to compare channel to channel, make everybody data having 0 to 1 only ataupun 0 to 100, so that you can compare easily lah. Okay, filter tu to remove all the artifacts. Segmentation, cut the data into shorter duration so that you can process segment by segment. Okay, the signal transformation you do in time domain, or you split into frequency domain, and then you look at both time and frequency domain. For frequency domain, you apply fast Fourier transform. For time frequency domain, you do wavelet transformation. You can do a short time Fourier transform. You can do empirical mode decomposition, and many other methods. So for frequency domain, the FFT is the basics for frequency analysis. The feature extraction is to find the information with the objective of characterizing the data or the event present in signal clearly. How to differentiate the normal ECG and the abnormal ECG. How to differentiate the resting EEG and concentration EEG. For example, you want to extract feature based on its energy, based on its complexity, based on the morphology, or based on the frequency. So you need to look at all. And from the many analysis, only use the most significant one. Then classification is done for identifying to which of a set of data observation belongs to, based on the threshold value, magnitude that must be exceeded for a condition to occur. If you do machine learning, you need to have supervised data and unsupervised data. So for supervised data learning, you need to label the data and learn and predict based on the learned data. This is normally the approach of artificial neural network lah. And also support virtual machine, knives-based method, and so on. Unsupervised learning, all data is unlabeled, and the algorithms are able to model the underlying structure, such as by using k-means clustering. So this one is the algorithm obtain the specific pattern they learn from the data collection itself. Okay. And for research in EEG, you do brain-computer interfacing. Brain-computer interfacing is to enable the signals from the brain to control some external activity, such as to move a wheelchair, to move prosthetic limb, and so on, to have music run, and so on. Computerized EEG screening aids the neurologist to detect EEG abnormalities, to identify seizures, brain tumor, and also for stroke detection. And they also do EEG studies for cognitive, emotional, and behavior study. The last one is normally done by the psychiatrist. So for those who have working in EEG, we have neurologists and psychiatrists. Psychiatrists also look at EEG signals, but their interest is on the cognitive and behavior lah. That's all regarding the EEG. I hope you can get the idea of how we can use EEG. So sekarang dah boleh fikir siapa nak buat EEG project, ECG project, and PPG. I try to make a collection of those three sets of data and give you all lah. So nanti saya bincang dengan Dr. Kalai on the project punya activities ni. So I stop here first and until we meet again on Thursday. So thank you guys with bear the time with me. Topic for quiz, basics of biosignals. Simple quiz je. Yang apa yang saya letak dekat UKM folio adalah general questions about EEG, about ECG, about nature, about basics physiology. Tak sampai lagi kepada signal processing. Yang tu mungkin kita buat next quiz ataupun actually I plan to have 2 quiz sebenarnya. My second quiz will be on electrical safety. Tapi saya tak sampai ke situ lagi.
Sorry Doktor, kuis hari Khamis ni?
Hari Khamis. Kuis pendek je, setengah jam. Tak sampai setengah jam pun.
Okay.
Saya kena simulate dulu. Sebab kuis saya akan buat, saya cuba embedkan Kahoot ke dalam UKM for You. So that selepas kuis terus ada skor dan saya tak perlu nak tengok balik. You all pun tahu jawapan dia apa for your punya learning. Hope it will be interesting. Okay guys. So thank you.
Okay, thank you Doktor.